Okay, let's do a kinematics example using gravity. Let's say that I want to figure out how tall the physics building is, or the science building is, Martin. So in order to do so, I'm going to go up to the top of the building and I'm going to drop my physics book off. I'm going to drop it from rest, at least to start with. Let's drop it from rest, and let's time how long it takes. And if it takes 3 seconds to fall to the ground, then how high is the building? And in addition, let's ask the question, how fast is it going when it hits the ground? So before we attack this problem through our regular problem-solving methods, I do want to address this how fast is it going when it hits the ground. What does that mean? Keep in mind that I did not ask how fast is it going after it hits the ground. How fast is it going after it hits the ground? Anybody? Anybody? Okay, so it's after it hits the ground, it's not going, it's stopped, right? It came to a stop. So what do we mean by how fast it's going when it hits the ground? What we mean is the instant it hits the ground, or the instant before it hits the ground. Keep in mind that what we're doing here is we're solving free fall problems. We're solving problems where, in this case, or constant acceleration problems, either way, we intend to be solving problems where, in this case, the book is undergoing only the acceleration due to gravity. There are no other forces. The moment it hits the ground, there are additional forces. What is the force? What additional forces are there when the book hits the ground? Anybody? Anybody? Okay, so there's the force of the ground up on the book. And does anybody know how big that force is? I certainly don't. I have no idea how big that force is. And that force is going to vary whether we land on grass or whether we land on gravel or whether we land on cement or whether we land on somebody's head. So we can't talk about the motion after it hits the ground, other than saying, yeah, we know it eventually comes to rest, but we don't know how fast it comes to rest, what the acceleration is, how much time it takes to come to rest. All we can talk about is the motion of the book while it undergoes constant acceleration, in this case due to gravity, before it hits the ground, from the time that we drop it to the time that it hits the ground. So, this is really important. When we ask the question, how fast is it going when it hits the ground, we mean the instant before it hits the ground, not after, not when it's going zero, but when it's still accelerating under the influence of gravity. Okay, so let's see how to attack this problem in general. In general, how do we attack a problem? The first thing we do is we draw a picture. And so here I've drawn a picture. Whoops. I've drawn a picture, and we let's label some things in the picture. Let's call the building a height h. And let's say we said already v0 equals 0. And we know that it accelerates in that direction at 9.8 meters per second squared. I don't know whether that's positive or negative yet. Why not? Because I haven't defined a positive direction yet. It's just always going to accelerate in the downward direction. And the displacement is going to be in that direction. So I might just, don't have to, but I'm just going to call that my plus x direction. So let's define my plus x direction as down. Think I've drawn everything in, I guess I drew an H, but I could draw a delta X, so it's displacing from the top of the building to the bottom of the building, and in time t. So we could draw all those variables in there. Okay, so then what's the next thing we do? We always draw a picture first, we label everything in the picture, we put arrows on the vector quantities, and then we write down our equations. So let's go ahead and write down our equations. Well, we know that delta x equals 1/2 at squared plus v0t. We know that v equals v0 plus at. We know that v squared equals v0 squared plus 2a delta x. Okay, so those are our three kinematic equations that we use. And then we identify what we know and what we don't know. Do we know what delta x is? And the answer is no. That's actually what we're asking in part A. So we don't know what delta x is, but we do want to know it. Do we know what A is? Yes, now that we've defined down as our positive direction, then the acceleration is the acceleration due to gravity, and as always, look at the direction of this arrow versus the direction of that arrow. If they're pointing in the same direction, then they've got the same sign. Let me get the right color here. Okay. So A is positive 9.8 meters per second squared in the x direction. Everything's in the x direction, so I won't bother putting that. If we want to, we could say in the x direction. I'll do that. And let's say v0. What's v0? Well, it was defined as 0. We called it 0. What is t? We don't know t. I haven't asked for t. We may not need to know t, but we don't know t. And what is v final? V final? What is v final? Do you know v final? No, that's what we're asking for in part B, right? V final is what is the velocity when it hits the ground or when it gets to the ground, just before it is stopped by the ground. Okay, so those are our 5 variables. And so then what we do is we start to plug in. And you will notice maybe that I called the height h. I also called it delta x, or I said, it's a height h, and I said the displacement's delta x. Well, in this case, h is delta x. We didn't have to define both of those variables, but h is delta x. So if you like, you can note that, or you could have just defined one variable or the other and recognize that h, whoopsies, that when we solve this, let's solve it in black, h, which is equal to delta x, is equal to 1/2 times plus 9.8 meters per second squared, t squared plus v0 t. Oh, well, that's not useful. Oh, so everybody's saying, wait a second, what are you talking about? You made a mistake. I can't wait to get extra credit. Well, I caught it before you did. Well, I probably caught it after you did. But t equals, T was given as 3 seconds. All of a sudden, I was like, wait a second. I can't solve this problem. I don't have enough information. T was given as 3 seconds. T was given as 3 seconds. So I can go back and I can say, oops, I do know T. It was a given. And I can plug it into this formula and say 3 seconds, 3 seconds. And so therefore, h is 44 meters. Plug into your calculator, h is 44 meters. And what we actually end up getting, again, when we're paying attention to the vector quantities, we end up getting a positive, and this was all in the x direction. It displaces 44 meters in the positive x direction. It displaces 44 meters in the positive x direction. Not so concerned in one-dimensional motion, but in two-dimensional motion, we'll be concerned about those directions. Okay, so how do we answer part B? How fast is it going when it hits the ground? Well, I think it's pretty obvious that we're just going to use either the second or the third kinematic equation. So that was part A. I'm just going to, so I don't have to go to a new page, just write part B in the corner, which you should never do this when you're turning in work. I need you to give yourself space, but so that I can keep everything on the page here, I can go ahead and say V equals V0. I'm going to use the second equation. V equals V0 plus A, 9.8 meters per second squared, times t, 3 seconds. And again, I didn't say before, but we should always check our units, make sure they work out. And so what we're left with is v final. V is v final, right? V is v final. That's by definition. Is 29.4, positive 29.4 meters per second. So the fact that it comes out to be positive 29.4 meters per second and everything's in the x direction, because we were talking about the x direction, what does that mean? What direction is velocity? Right? The velocity is down. Velocity is down the whole time as it falls. Okay. So, so now I'm going to ask a part C. I'll do that on a new page. Part C is, I'm going to change this up. What if instead of dropping my book from rest, I now throw it down with an initial velocity of 5 meters per second and ask, now if I throw it down, how long does it take to get to the ground? So we already know part A and B. I'm not saying anything's changed here. Well, what has changed is if I throw it down, it's no longer going to take 3 seconds, right? That 3 seconds was for starting from rest. Okay, so keep that in mind. So part C is... Okay, so here we go. This is the problem statement. So I did that. Now I take the book back to the top and throw it down with an initial speed of 5 meters per second. How long does it take to fall? Well, so we can go back to that initial picture and we can redraw it. So for part C, maybe I'll do it in red. For part C, what has changed is V0 equals 5 meters per second in the downward direction. And what's changed is that it no longer takes 3 seconds to fall. That was dropping it from rest. Otherwise, I believe everything else is the same. So, actually, let's just be careful, right? The height of the building is still the same, but the final velocity is not the same, right? This changes. I didn't ask what the final velocity is when I throw it down at 5 meters per second, but it does change. Okay, so there's my picture. I've written down what I know and what I don't know. So when I look at my equations, we still have the same three equations. Delta x is now, we know it's plus 44 meters. So this is for part C. A is still that. V0 is now plus 5 meters per second because it's in the downward direction and down is positive. T is an unknown. V final is an unknown. And there we go. So that's what we know and what we don't know for part C. If you wrote that all out separately for part C, that might be more clear to you if it's a little unclear here. Okay, that's not true for part C. Okay, so we can go ahead and we can use the first equation, the first kinematics equation, to say, okay, that means that 44 meters equals 1/2 times 9.8 meters per second squared. T is now an unknown, plus 5 meters per second times T. Say we want to solve this equation for T, right? There's one equation, one unknown, so what does T equal? Now this is where, right, this is going to come up all the time. We need the quadratic equation. So this is where you need to be able to apply you need to know and apply the quadratic equation. I actually, if I give an equation sheet, I always put the quadratic equation on an equation sheet. So I don't think you necessarily have to memorize it, but it comes up so commonly, it's a good idea to know that the quadratic equation in general, so aside, let's do it yet another color. Quadratic equation in general says that if ax squared, let's not use x because that's our position variable, a times some variable, well, let's use t. At squared plus bt plus c equals 0, where a, b, and c are arbitrary constants and t is an arbitrary variable that we're solving for. Therefore, the quadratic equation says that t is minus b plus or minus the square root of b squared minus 4ac all over 2a. So what that ends up giving us is when we plug that in to the quadratic equation, we indeed get that t equals 2.53 seconds and minus 3.54 seconds. Two answers, and be very careful because sometimes both answers are correct, sometimes only one answer is correct and the other one is non-physical. In this case, which one or both are correct, and the correct answer is 2.53 seconds because minus 3.54 seconds happens before I ever drop my book. So that's not a physical answer. So the answer is 2.53 seconds. Again, just to make sure you understand, I got this by taking this equation and making it look like a quadratic equation, right? 1/2 times 9.8 t squared plus 5t minus 44 equals 0. So this was A, this was B, and this was C. Plug that in there. I dropped my units just for neatness, just to show how the quadratic equation worked there. Let me ask one more question about this answer, and that is, what does the minus 3.54 seconds mean? It's not just an arbitrary answer. Why was there a second answer of minus 3.54 seconds? And that means that if the book was undergoing the same motion before I started the stopwatch, then it would have been in the same place 3.54 seconds ago. Meaning, right? So look at this motion. If instead of the problem that the way it was just stated, if instead I was at the ground and I threw the book upwards and it went up and then came back down, so that at this point the book had a speed of 5 meters per second in the downward direction, then it's this, Let's make sure it's clear. It's this trip that took 2.53 seconds. Whoops. 2.53 seconds. And it would be this trip, right? The one that goes up and there. That trip that took 3.54 seconds. 54 seconds, right? But in this problem, we only just started at that point, right? We only just started at that point. So the other answer was actually a potentially physical answer. It's just that the book was not undergoing any motion prior to the stopwatch when we started the stopwatch at t equals 0. Okay.